Welcome everyone. In this video I'm going to talk about the Euler angles and the orientation matrix. And this topic is very important for texture analysis. So when you are investigating the microstructure of your specimen, for example some metals or some kind of minerals, you want to know what is the inner structure of the individual grains or how they are oriented respect to a specific coordinate system or something, then this topic is very useful for you. So basically what you can see at this corner, that's the most important part. So we have a piece of slab or sheet here, and we attach a coordinate system which is drawn in red. So basically the three-dimensional axis here, we have the x, and we will call it as the rolling direction, and we have the y-axis. This will be the transverse direction, and these two are perpendicular. And then we have another z-axis or the normal direction. So this if this is a vector, then this vector is perpendicular to this plane. So basically the normal vector of this RD-TD plane. And then I have these small letters here, XS, YS and ZS. This is basically just that these three coordinates belong to the specimen. So we fix a coordinate system to the surface of the specimen. And then we have crystals. I just drew two different crystal orientations, let's say. So within this big piece we have individual small, let's say, grains, and the grains of these materials are oriented in a specific direction depending on the history of the material. So basically you can control it somewhat with the process, rolling, annealing and things like that. And each of these individual grains have their own specific coordinate system. And I use a small c here as crystal, so xc, yc and zc. And wherever you will have grains within the material, they will be oriented in a different direction, and they will have their own coordinate system. And the good thing is that there are an obvious relationship between this coordinate system, the green one, the crystal coordinate system, and the specimen coordinate system. And this relationship can be described with three consecutive rotations. So if you can define the coordinate system for your specimen, then you will be able to get the information for each grains within your specimen. Then that what I just basically wrote here. So we have the set of coordinates for the specimen, and there is a matrix here. Let me just write it down. So this is a matrix, actually a 3x3 rotation matrix, which can help us to express the coordinate system in another coordinate system, so within the crystal coordinate or vice versa. So if we use these three consecutive rotations, they are described by these so-called Euler angles. So these are here, phi 1, capital Phi, and phi 2. And in the bottom we can see it. So let's start here. So this is the first part. So here we go from the case when the two coordinate systems are aligned. So you see that Z, Y and X are all aligned. So then the first thing is that we rotate the system just along the z-axis. So you can see it on the second image. So we did a rotation, which is the phi 1 here, rotation along the z-axis, and you could see that the original s-axis moved here. So now we have the red is the crystal axis, so we see that a phi 1 rotation moved the x and the y, because basically the z-axis is perpendicular to the xy plane. So if we rotate around the z-axis, then we move the whole plane, so we rotate the plane. So basically that happened here. So both the x and the y-axis was rotated by phi 1 angle. And then now we jump from here to the third step, where we go to this y-axis. So we go to the x prime c-axis. So here in the third step we rotate around this by a capital phi angle. So what we can see that first of all, which is the easiest to capture, is that we rotated the z here. So now it's off, and the two z-axes are not parallel anymore, and we have this phi angle. And then from the previous step, here was our y prime. So we now have a phi, capital phi rotation. So the y just left this xy plane, so it went up, and with of course the same angle as the zc. So this is our, let's say, step 3, or the third state of the two coordinate systems. And now we go back to the z-axis again. So we are here, and we apply a phi 2 rotation around the z prime axis. So you can see the previous state, or the previous position of the coordinate system axis was here with the dashed line. So now we moved the xc out of the plane, we can say like that, and that is the phi 2 rotation. And then here we can see the history of the y-axis. So first we had the phi 1, and then that happened in the same plane, and then we moved out of the plane with the capital phi, and then again with the phi 2. So the final position of the phi of the y prime is here. So you can see that basically first we rotate around the z-axis, or the normal direction. So we will have a different rolling direction and a different transverse direction. And then this was the phi 1, and then we use the capital phi around the changed so here around the changed rolling direction, basically, because this axis can be said as the rolling direction. So as we can see that this stays the same, but then the y and the z, or the TD and ND is changing. And finally we go back to the z, or the normal direction again, and we have a phi 2 rotation, and that's all. So basically this is all. And these 3 rotations, so this is basically the first rotation, but number 2 is used just because to show you that this is the second state of this process. So the first rotation, the second rotation, and the third rotation can be described by a matrix. So now I show you those matrices. So we came back to the figure. So I just put up the Euler angles and the coordinate systems up here. So here are the matrices for the rotations. So let's call it G. So the G phi 1 is described by this matrix, and this is a phi 1 rotation around the z axis. And then the second rotation is G capital Phi. This is basically the capital Phi rotation around the xc axis, so around this here. And then the last rotation is the G phi 2, which is a phi 2 rotation around the zc axis. So we are here again. So we can combine these three consecutive matrices because we can just multiply them easily and apply this rotation on the specimen coordinate system or the specimen coordinates. So basically that's what we see here down. So we have we want to let's say express the SC, so the coordinates in the crystal coordinate system. So we just go and multiply these guys together and then multiply it. So this is basically how you apply the operator, because this big 3x3 matrix is basically an operator, and then this can be, let's say, either a matrix or a vector. So this is now, let's say, a vector. So we apply the matrix on the vector. This is just simplified. And at the end we get back the SC. So here this big matrix is basically just the product of this multiplication of these three guys here. So 1, 2 and 3. And we usually write it as G phi 1 capital Phi phi 2. So this is quite simple. If you have these three Euler angles, you just plug and chug everything here. So you see where's the phi 1, phi 2, whatever, and just solve it. So this was quite simple, and you could see that the three consecutive rotations can be described by three 3x3 matrices, and at the end you can apply this at once by a huge matrix, which is still 3x3, but it has a lot of long, let's say, formulas in it. But it's very simple because you just put in the correct numbers. One mistake that you can do is you have to decide whether you are using angles or radians. So you have to make it clear in the beginning of the process, because otherwise you will just mess up everything. So now we have this, and what we can do, I can show you a very simple thing how you can use this orientation matrix or rotation matrix. This is just one example, but I will show you several more later on. So I just moved the matrix from the previous picture here, so we just have to take care about this. And one nice property of this matrix, that if we take the first column of the matrix and the last column of the matrix, we can get the HKL coordinates and the UVW. So basically we can get the plane and also the direction. And what we have is just we just calculate the components of this. So it's just straightforward. You imagine these as a 1x3 matrix or a 1x3 vector. So this is very simple. And just an example how we can use this. So this will take some time, but I just try to write it down nicely. So let's say we show an example. So we have our matrix. So this is basically G phi 1 and then capital Phi and phi 2. So we just take some numbers and I show you how to proceed with this exercise. So let's say you get an example from a crystal, or you just get an exercise in the exam where you get a rotation or orientation matrix. So, and then usually you will have a 3 by 3 matrix, and this is what you will have to do with this. So I'm just writing down the numbers while I'm talking. So basically, as we discussed on the previous slides, then these matrices are used to describe the relationship, the rotational relationship between two coordinate systems, which are the sample and the crystal coordinate systems. And this is what we get. So basically this is 1 pixel or 1 point on your specimen, and each point on your specimen has a specific matrix with a specific set of values, and this is 1, let's say. So if we just check the matrix up here, we will use the first column here and the last column here, and let's start with the first one. So the first one here, I'm just trying to highlight it, this will be the HKL, and then so this is, I'm just collecting the numbers again to make it more understandable. So this is 0.508 and this is 0.648. So here what you try to do is you try to find the closest integer of this. And what I would do, I would pick the largest number. So in this case is this guy here, 0.648, and then divide all of these guys with 0.648. So you divide everything, and then you will see that it will look like this. So this is what we have here, and then once we have this, let's just write down the numbers. So this is, let's say 88. I'm rounding the numbers slightly. This is 79, and this is 1. So we round up these numbers, so this will be the 111 here. And then we do the same practice with this here. And we have the U, V, W, and then we do the same. I'm trying to save some time. So we know that the largest number here, there are 2 negatives, but we don't care about the absolute value, so we take the 0.7. So the first letter or first number is 0.7 divided by 0.7, and then minus 0.712 divided by 0.7, and then minus 0.054, 0.7. So we have this, and we don't bother with the exact numbers. First I showed you just how to do this rounding up. So the final of the UVW is that here we see that this is 1 and this is minus 1. So we put a line here. This is minus 1 and this is 0 because it's very, very small number. So basically the final result is that if we do like HKL and UVW is 1, 1, 1 and 1, minus 1, 0. So this is our final. So from the orientation matrix we can get the HKL UVW values, which is basically the texture component. So the point with this orientation matrix will have the 1, 1, 1, 1, minus 1, 0 texture component. And this is just one example what we can get from the this G matrix. So in the next video I'm going to show you how you can get the Schmidt vector in a real case by using the Euler angles and then calculating the G matrix based on the Euler angles, and how you can use that to represent the stress, the external stress, as a resolved stress, and how we can calculate the Schmidt vector. And this is one example, and I will also show you how to calculate the misorientation between 2 points, where we basically just take the two matrices and we apply some rules, and we will able to get the misorientation. And this is good because, for example, we can find grain boundaries if we do a backscattered electron diffraction map of our specimen. And later on I will show you how this works in the reality. So this is all. It was quite simple. I just showed you the description of the orientation matrix or rotation matrix, how this describes the relationship between the two coordinate systems, which is the specimen and the crystal coordinate system, and then how we can use this rotation operation or rotation matrix to extract more data for our material. And then this data is basically, one of these data is basically the texture component. So I hope that this was useful for you and you learned something, and see you in the next video.